Good evening, everyone. I welcome you all for this week's discussion. Today, we are going to focus on uh, regenerative type heat exchangers. So, we'll first build some background about regenerative type heat exchangers. It is that kind of heat exchanger which is a storage type, and the same space is occupied alternatively by both hot and cold fluids. This is different from the other types of heat exchangers that we have studied. They were mostly recuperative type. That means we had inserted one copper tube, one tube inside the other tube, and both had different flow paths. So here one fluid flew, and in the annulus section I can say that there was another fluid that was flowing. But here we are going to see that kind of heat exchanger where the same space is occupied by both hot and cold fluid alternatively. So in this kind of heat exchanger, the hot fluid initially transfers some part of heat to a matrix or a packing material that is already filled inside the flow channel, and during the next cycle the cold fluid picks up that much heat in the alternating cycle. If we can recall, there were three configurations of heat exchangers based on flow direction, that was parallel flow, counter flow, and cross flow. But here in these kind of regenerative type heat exchangers, there is no concept called cross flow heat exchangers, because in cross flow we had two different fluids flowing at right angle to each other. But here we only have a parallel flow regenerative type heat exchanger or a counter flow regenerative type heat exchanger. So we can divide this regenerative heat exchanger into two categories. First one is called a fixed bed or a valved type regenerative heat exchanger, and the second one is called a rotary regenerator. We will focus only on this one in this class. So as I have told you that we have a tube or a flow channel which is filled with matrix. This matrix is actually a material with high specific heat capacity, because we want to store more amount of energy. So based upon the temperature that we want our heat exchanger to operate, the matrix material will be different. For example, if we want to the heat exchanger operating at 10 to 30 Kelvin, we would be requiring lead and lead antimony spheres or lead antimony shots to be present in the matrix. In case we want the heat exchanger to be operating in the temperature range of 100 to 300 Kelvin, we will be using SS material as the matrix. Below 10 Kelvin, there are other types of magnetic materials that we are going to use. So broadly, if I can tell, between 10 to 30, it is lead which is going to be used as the matrix material. So the tube or the flow channel is filled with lead shots depending upon our requirement of pressure drop or the pressure drop that we can accommodate. The diameter of the spheres are also going to be used or also be calculated. So the hot stream first flows in this path and heats this matrix material and passes away through this portion. Now once we close these valves, the cold fluid then goes into this matrix material and passes and picks up some part of heat energy from the matrix material and goes away. So in this fashion, the hot and cold streams pass alternatively in the same matrix, giving rise to regenerative type action, so hence the name. So this is a fixed bed or valved type regenerator, which we are going to discuss in this class. We also have another type. I have put it just for the sake of completeness. It is a rotary type regenerator, where we have the matrix material fastened over a shaft. So initially the hot stream passes, and then because of the rotation of the shaft, the hot matrix comes down by 180 degree or rotates by 180 degree because it is on the shaft, and the cold fluid then takes up that amount of heat, giving rise to a heat exchanger effect. If I can give few examples of matrix type fixed bed regenerator, we have pulse tube cryocoolers. These cryocoolers are generally refrigerators which can provide few watts of refrigeration at temperatures less than cryogenic temperatures, that is less than 123 Kelvin. So helium is employed as the working fluid in that pulse tube cryocooler. It is in cryogenic engineering, this pulse tube refrigerators are commonly used. So coming back, the performance of these heat exchangers is actually a function of the mass of the matrix, the specific heat of the matrix. This is obvious because if the specific heat of the material at that temperature is low, there is no point in putting a large amount of matrix material. Also, the frequency of switching of flow, that means for how much time should the hot fluid pass over the matrix, and for how much time the cold fluid is going to pass over that same matrix. So this frequency also matters, in addition to other known parameters such as heat capacity ratio, that is C min by C max, and also the number of transfer units of this heat exchanger. So there are 5 different parameters on which these regenerative type heat exchangers depend on. So there are few advantages, and obviously it comes with a major disadvantages too. So the major disadvantage being the mixing of the fluids during the switching process. So once we have to change these valve positions to alternate between the cycles of hot and cold fluid streams. So however, in case if it is the same fluid such as nitrogen or helium, the degradation could be smaller. In case if the hot and cold fluids are two separate fluids, say nitrogen and helium for example, so we'll have a problem at that point because helium and nitrogen are going to mix. So that is one major problem which we can't avoid. And also for rotary regenerators, there is a problem of leakage, and sealing becomes a very difficult issue. The problem with sealing, if the sealing is inappropriate, and if the hot and cold fluid streams are at different pressures, say at a pressure of 10 bar and 1 bar, so there is always a risk of mixing of these two fluids when there is no proper seal. So in rotary heat exchanger, rotary kind of regenerators, this problem becomes a huge effect. Also, I would like to focus that these type of heat exchangers are mostly gas to gas based heat exchangers. So I'll give you one numerical problem to work out. We have a regenerator that is constructed with 1.88 kg of metal spheres having a specific heat of 840 joule per kg Kelvin. The thermal conductivity is also given. The heating and cooling periods are 4 by 3 seconds each. So the total regeneration period is 8 by 3 seconds. The fluid employed is helium gas, whose properties are also given. On both hot and cold fluids, it is helium gas with a mass flow rate of 40 grams per second on the hot side, and on the cold side it is 36 grams per second. The heat transfer coefficients on hot and cold side are also given. The areas are also given, heat transfer surface areas. We want to determine the regenerator efficiency, regenerator effectiveness. I'll give you a few minutes of time. You can work out and I'll show you the solution. So I'll keep telling you a few hints. The first step is to find out minimum heat capacity fluid. So minimum heat capacity fluid is m dot cp. On hot side we have helium and on cold side also we have helium, but the mass flow rates are different. You can take Cp of hot and cold fluids as the same. So m dot Cp of hot and m dot Cp of cold fluid stream we have to find out and then see which one is the C minimum fluid. Can you tell me the heat capacity of hot fluid? CH m dot Cp of hot fluid.
Wait a minute, wait a minute. So it is coming around 33.6. 33.6.
C hot is defined as like this, m dot Cp of hot fluid. So m dot here on hot fluid is 40 grams per second. So 40 into 10 power minus 3 multiplied with 5200.
0.84 kilojoules.
Can you tell me for the hot fluid?
CP. It is 52. It is 208.
Yeah, it is 208 watt per Kelvin. So can you similarly can you find out Cc?
Wait a minute. So it is coming around 187.2.
Yeah, 187.2 watt per Kelvin.
187.2.
Next we are going to find out, so obviously Cc, that is the cold fluid, is the minimum heat capacity fluid. So we are going to find out the heat capacity ratio Cr, that is defined as C min by C max.
It's coming around 0.9.
Yeah. So C min by C max, that is the heat capacity ratio, comes out to be 0.9. So it is not a balanced flow. If it were a balanced flow, the C min and C max are same. So for a non-balanced flow, we are going to use a different kind of approach than the conventional one or the straightforward one. So the next step for us is to find out the NTU of this heat exchanger. So that is defined as UA by m dot Cp min. So NTU is defined as UA by m dot Cp min. So I can write UA as 1 by HH AH plus 1 by HC AC to the power minus 1 multiplied with 1 by C min. The denominator is already known,
Yeah, yeah.
187. So
187. Yes, the coming NT is coming around 21.1.
yeah, correct. Are there any other participants?
Okay. No, Mr. Sanjay is there.
Yeah. Any other questions here up to this point?
No, sir. No, sir.
Okay. If there are no questions, we'll keep carrying forward. So the NTU of this heat exchanger comes out to be 21.11. So we found that as UA by m dot Cp min. M dot Cp is straightforward, m dot Cp of cold fluid. So we found out UA as 1 by HAH plus 1 by HCAC raised to the power minus 1. So NTU is 21.11. So next up what we are going to do is we are going to find out the matrix capacity ratio. That means the matrix is also going to store some part of heat, which is uh, a characteristic. So that we are going to define as mass of the matrix or sphere multiplied with specific heat of the sphere divided by the total time P naught into C min. The C min is already known, 187. P naught, that is nothing but the total time period, regeneration time period, that is 8 by 3, it's already given, and ms into cs, that is ms is the mass of the matrix, that is 1.882 kg. Cs is the specific heat of the solid material that is used. So it is 840 joule per kg Kelvin.
It is coming around 3.1, sir.
Can you repeat it?
3.17.
Yeah, it is 3.167. That is right. So next what we are going to do is uh, if this was a balanced flow, what we would have done is for CR being 1 and for certain heat matrix capacity ratio. For example, we'll take a case where matrix heat capacity is 3 and NTU say is 50. It is not pertaining to our problem, but in case if we were lucky enough to have this situation where CR equals 1, this is the procedure we had to follow actually. So NTU of 50 and matrix heat capacity ratio of 3. So we would have directly got the effectiveness of heat exchanger as 0.975. But in our problem, we don't have this condition. So what we are going to do is, we are going to find out the effective NTU and effective matrix capacity ratio. So effective NTU is defined as 2 times CR into NTU divided by 1 plus CR. So this is the definition of effective NTU. I denote it as NE. Can you evaluate this one? NTU was 21.1, CR is 0.9.
It is coming at 19.98.
Good. It is 20. We can take that as
Almost.
20. Okay. So we have 1 point with us, that is NTU. So next we are going to find out the effective matrix heat capacity ratio ME. So that is defined as 2 times CR into CM divided by 1 plus CR. CM we have already CM we already know. CR is 0.9.
It is coming around almost 3.003. So we will take it as 3.
Yeah. So any other questions by any other participants? Okay. So we have 2 points with us, that is effective NTU and effective thermal matrix heat capacity ratio. So what we are going to do is, for matrix heat capacity ratio of 3 and NTU 20, we will find out what the apparent effectiveness is. I may call it that way. So it is not the actual effectiveness. So for matrix heat capacity 3 and NTU 20, so I have an effectiveness of 94 point. I have an effectiveness of 94.3. So when I have an effectiveness of 94.3, I 0.943, I name this effectiveness as epsilon 1 and find out a parameter called x. So x is defined as 1 minus CR whole squared by 2 times CR into epsilon 1 by 1 minus epsilon 1. Can you plug in the value of 0.943 and evaluate parameter x? Any answers?
So it is coming around a negative answer, minus 23.61. Yeah, okay. Which CR we have to take, whether the rounded value or say 3.1?
No, CR was the heat capacity ratio of the fluid, that was 0.9.
Yeah,
C min by C max.
yeah, yeah. So it is coming around 1.746.
Yeah. So we get a parameter x, which is 1.746. Now, based on this parameter, we are going to find out the actual heat exchanger effectiveness, which we want as per the question from this formula. Epsilon, or the actual regenerator effectiveness, is 1 minus e to the power minus x divided by 1 minus Cr into e to the power minus x.
The effectiveness is coming around 0.979.
Yeah, that is correct. We have an effective heat exchanger effectiveness of 97.93 percentage, or 0.973. That is right. So I'll quickly recap the procedure that we followed. So first, for these type of problems, what we are going to do is we are going to find out the minimum heat capacity fluid by finding out m dot Cp of that fluid. Luckily, we had Cp as same, as 5.2 into 10 cube joule per kg Kelvin. However, the mass flow rates are not same. One, on the heating side, we had 40 grams per second, and this was 36 grams per second. So now we are in a position to find out C min and C max. After finding C min and C max, we are going to find out the heat capacity ratio, which is denoted as Cr, as C min by C max as 0.9. I'll put this for a minute later, and I am also going to find out my NTU of this regenerator, which is UA by m dot Cp min. So because HAH and HHAH equals HCAC, I have written it as 2 by HA. I know all these values. I plug in these values to get an NTU of 21.1. I find out the matrix heat capacity ratio, which is Ms by total regeneration time into C min. That comes out to be some value 3.1. So because my heat capacity ratio is not equal to 1, I need to find out effective NTU and effective CME, and then find my effectiveness. However, if my CR was equal to 1, I could have directly got the effectiveness for a counter flow regenerator directly from this table given by London. Okay, so to find out the effective NTU from the calculated NTU, we are going to use this formula 2 times CR into NTU by 1 plus CR. So we get a value of NTU as 20, and similarly we are going to find out effective matrix capacity, that is 2 times CR into CM by 1 plus CR, we get it as 3. So from the table given, we are going to find out the apparent effectiveness, if I may call. This is not the actual effectiveness, so that is 94.3 percentage or 0.943 as given in the table. So I need to find out a parameter x, which is defined in the fashion shown on my screen, 1 minus CR squared by 2 times CR into epsilon 1 by 1 minus epsilon 1. So that I end up with a value of x being 1.746, and to find out the actual regenerator effectiveness, I use x and CR values to find out actual regenerator effectiveness as 97.93% or 0.979%. Any questions?
No, no, sir, no, sir.
Okay. If there are no questions, we'll take up one more problem from Baron, cryogenic heat transfer by Baron. We have a regenerator which is constructed with metal shards of 1.5 mm diameter, having a density of 7,800 kg per meter cube, and the specific heat is given. It is enclosed in a tube of ID of 40 mm. The porosity of the matrix is 0.4. The heating and the cooling periods are 2 seconds each. They have employed helium as the fluid at an average temperature of 190 and at an average pressure of 405 kilopascal or 4 bar. The mass flow rate is same during heating and cooling time of 35 grams per second. We want to find out the heat transfer coefficient of the fluid. So we have been given, I have given you the heat transfer coefficient in terms of a relation, that is Colburn J factor, and the properties are also given. So to find out the heat transfer coefficient from this formula, we need to find out the Reynolds number. That is our first target. So Reynolds number is defined as GD by mu. The denominator is known, dynamic viscosity, so it is also known. So we are required to find out the mass velocity g. This diameter is also known. This is corresponding to this diameter 0.15 1.5 mm. So we are now down to one problem of finding g, that is mass velocity. So mass velocity, I define it in this way: m dot by free flow area. I know m dot, that's already given in the question. Now again I am down to finding free flow area. Again, I write the free flow area as void fraction or porosity, if I may call, porosity into a frontal area. Again, I am down to finding frontal area because the void fraction or the porosity is given as 0.4. Next up, what I do is I am going to find out a frontal area as pi by 4 into 40 mm squared. So from this point, we are going to start. So can you calculate the frontal area? Pi by 4 into 0.04 squared.
It is coming out 1.256 into 10 power minus 3 meters square.
Okay. Can you put the frontal area in free flow in this formula and find out the free flow area?
It is coming around the 0.35. G is 0.35, 0.035.
Frontal area?
Of wait a minute, rental area is 1.256 is at 4 minus 3 meters square, and G, G is coming around 0.035. G value. Mass velocity.
Can you tell me the free flow area?
Free flow area. It is coming on 5.024 10 power minus.
Yes. Free flow area is 5.024 into 10 power minus 4. That is absolutely correct. So that we are going to put in this formula of G. M dot is uh, 35 grams per second. So it is 0.035 kg per second divided by 5.027 into 10 power minus 4. So we are going to have a G value of 69.93.
69.66. 69.94. I have 69.66. No problem. 69.9.
Okay. So after finding out the value of G, we are going to plug the value of G in Reynolds number as GD by mu. Uh, we know G 69.63 kg per meter square second. D is also known, that is 1.5 mm, and dynamic viscosity is 14.45 micropascal second.
It is coming around 7,000
Yeah,
and
correct.
228.027.
Correct. Can you plug that value in this formula of J and find out what is
Yeah, yeah.
J?
It is coming around 0.018.
Yeah,
1838.
correct. It is 0.01790, so it is fine. So Colburn J factor is defined as H into Prandtl number power 2 by 3 by GCP. This is what we want, heat transfer coefficient. Prandtl number is given in the question. Cp is known to us. G also we have calculated. J we have calculated now. So can you find out heat transfer coefficient now?
Once again, need the value of Prandtl number. Not this point. It is coming around 1397.
Maybe there is a calculation mistake. Uh, so I'll just maybe in the last step it is erroneous. So I'll just repeat what we have done. Uh, First, we are going to find out the frontal area, that is pi by 4 into ID, tube ID whole squared. So we'll get a value for frontal area. So the free flow area of the regenerator is calculated in terms of uh, porosity multiplied with frontal area. So we end up with some value of the free flow area for the regenerator, and we find out the mass flux, or we can call it as mass velocity, as m dot by a free flow area, cross sectional area. So that comes out to be 69.63. After finding out mass velocity, we are going to plug that value in Reynolds number to get a value of 7228. After getting this value of Reynolds number, we are going back to the correlation given as in terms of Colburn J factor. So once we plug the value of Reynolds number, knowing the value of porosity, we get Colburn J factor as 0.01790. So Colburn J factor is nothing but Stanton number into Prandtl number power 2 by 3. Stanton number is nothing but H by GCP. Knowing all other values, Prandtl number is given, mass velocity is calculated, Cp is also given, Jh is calculated. So we end up having the heat transfer coefficient as 8423 watt per meter square Kelvin. Any questions here?
We have normally taken the value of CP value.
Okay, fine.
All our points are correct, and we have taken the value of CP of shorts, shorts value.
Cp of
Prop metal shorts 840.
Oh, okay, okay.
I cannot
No,
take
no, no.
that.
It was for the fluid.
Uh,
We are going for the
yeah, yeah.
fluid.
I understand.
Yeah. If there are no other questions, we'll take up one more numerical.
Yeah, thank you. One more question. Please proceed.
Okay. Uh, so far, we were discussing about the effectiveness NTU method in both problems, first problem which we have seen. There is also another problem called lambda and pi method. Uh, but in fact, both analysis give the same result. We can also check one of the worked out problems in R.K. Shah textbook, and also in Barron there was one more exercise problem just before this or just after this 5.17 or 5.18, where he also advises to use lambda pi method, or else we can go for effectiveness NTU method also. Both will give the same final answer. So using the effectiveness NTU method which we have learned, we are wanting to find the effectiveness of a bed type packed type regenerator having a matrix material of certain specific heat and certain mass. The mass flow rate of the gas during the heating period is 2 kg per second, and during the cool down period, during the cooling period, it is 1.8 kg per second. The specific heat of gas is same for both heating and cooling periods, that is given. The total period or the regeneration time which we call is 9 minutes. The heat transfer coefficients for heating period is 416 watt per meter square Kelvin, and for cooling it is 388 watt per meter square Kelvin. The surface area AH and AC, which we call, they are equal to 108, it is equal to 108 meters square for each period. So I'll give you a few minutes to try this problem and determine the effectiveness of the heat exchanger. It is similar to the problem 1. First, we are going to find out the minimum heat capacity fluid, then NTU, then matrix heat capacity ratio, effective NTU, effective matrix heat capacity ratio, going back to the table and finding apparent effectiveness, not the actual effectiveness, finding out parameter x and then plugging the value in effectiveness. It is just one step more, because previously we had heat transfer coefficients on both sides as equal, but this is not equal. Okay, I'll go through the solution procedure. It is quite similar to first one. I'll go through the procedure. So first, what we are going to find is the C max and C min of the two fluids. So the flow rates are different, though the Cp is same. So for one fluid, that is a hot fluid, we are going to get C max, and for the cold fluid, we are going to get C min. Next up, what we are going to do is to find out an NTU. It is nothing but UA by m dot Cp min. UA is nothing but 1 by HAH plus HCAC to the power minus 1. In the previous problem, we were lucky enough to find that HA on hot side and HA on cold side were equal, but in this problem it is not. So we are going to plug the values of HH that is given in the question and HC, which is also given in the question, multiplied with AH and AC, both equal to 108 meter square. So we end up having an NTU of 11.89, and we are going to find out the matrix heat capacity ratio as MSCS by Cmin into regeneration time, or we were calling it as P naught. So uh, dimensional stability should be there. So it was given as 9 minutes. We are going to be very careful in these type of situations. So we end up having a matrix heat capacity ratio of 1.319. So we are going to have a heat capacity ratio of 0.9, and then we are going to find out the effective NTU. We already know the formula, 2 CR NTU by 1 plus CR. We end up with having an effective NTU of 11.264. These are we are conversant with this formulae. And also effective matrix heat capacity, that is 2 CR Cm by 1 plus CR. So we are going to get an effective matrix ratio of 1.2 or 1.25. So we'll go back to the table uh, of London, Cottage and London, and find out for 1.25 and an effective NTU of 11 to be around 85.51. It is not an exact one. To find out an exact one, we need to interpolate between the values. So as I just wanted to show you the procedure, so I have taken an NTU of an effectiveness of 85.1 corresponding to an NTU of 10 and 1.25. So after finding epsilon 1 or the apparent effectiveness, it is not the actual effectiveness, we are going to find out a parameter x. Again, this formula also we are conversant with our first problem, 1 minus CR squared by 2 CR times epsilon 1 by 1 minus epsilon 1. So we get a value of 1.158, and this is the one which is the actual heat exchanger effectiveness. So we can just plug the values of x into this formula and get the value of actual heat exchanger effectiveness.
95.6.
95.6.
Yeah.
It shouldn't
That
be
is
so
0.9.
off because it is just 85.1.
Yeah,
What was your NTU?
NTU, EAT, more or less the same. More or less same.
Effective 11.89. It shouldn't be 90. I to my thing, it I don't think it should be around 96.
Yeah.
Just you can check your calculations once again,
Yeah,
because epsilon 1 is 85.1.
yeah,
Yeah.
yeah.
Okay, shall we proceed to the next one? Next
Yeah,
question.
yeah.
Yeah. This is also one of the exercise problem from uh, cryogenic systems by Parent textbook. We have nitrogen at 200 Kelvin and an average pressure of 5 bar, that is flowing through a regenerator matrix of 3 mm diameter with a mass flow rate of 20 grams per second. The porosity is 0.4 and the matrix uh, ID is 80 mm. Tube ID is 80 mm and a length of 750 mm long. The properties are all given for nitrogen at 200 Kelvin and 5 bar. So we want to determine the pressure drop of the nitrogen flowing through the regenerator. So for finding out the pressure drop, uh, I'll give you a correlation which is based on the friction factor, that is friction factor F is 5.375 into Reynolds number power minus 0.14. This is valid when Reynolds number is greater than 1000 and only for packed bed of spheres, because we can have different matrix materials like woven SS, woven lead, etc. but wire meshes, but this correlation is only for packed bed of spheres. I'll give you a couple of minutes to just think over it and I'll show you the solution. So what we are going to do is to find out, for finding out delta P, we have to find out friction factor F. For finding out friction factor, we need to find out Reynolds number. That is our first target. So for finding out Reynolds number, we need to find out G, that is mass velocity. So to find out G, we need to find out G is nothing but m dot by free flow area, or I can write that as m dot by porosity into frontal area. I know frontal area, that is nothing but pi by 4 into ID of tube squared. So pi by 4 into 0.08 squared is nothing but my frontal area. That multiplied by porosity gives me of 0.4. On the numerator I have 20 grams per second. So I am done with calculating my value of mass velocity. So after finding out mass velocity, I go one step forward to find out the Reynolds number, Gd by mu. Now, to find out equivalent diameter for a packed bed sphere, this is only for a packed bed sphere formula, that is nothing but 2 times porosity multiplied with the diameter of that spheres divided with 3 times 1 minus porosity. So 2 times porosity multiplied with diameter divided by 3 times 1 minus porosity. So I have a equivalent diameter of 1.3 mm. You can calculate and check it later also. So after finding out my equivalent diameter, I plug that value in this formula where I have G. Now my G is nothing but 9.9 once we calculate in this place, and mu is already known. So Reynolds number comes out to be 1021. So I'll again go through. So I am first calculating the equivalent diameter from this using this formula, 2 times porosity into diameter of each sphere divided by 3 times 1 minus porosity. This is only true for packed spheres. I have 1.3 mm as my equivalent diameter. Next up, I find out mass velocity m dot by A free flow area. Free flow area is nothing but porosity multiplied with frontal area. I get a G value of 9.9 kg per meter square second. Now after finding out G, I know the formula for Reynolds number as G times D by mu. So I get a Reynolds number of 1021.78. Obviously it's a dimensionless parameter. So for packed bed of spheres having Reynolds number greater than 1000, I have this correlation for friction factor 5.375 multiplied with Reynolds number power minus 0.14. So I get a friction factor of 2.038. Now once we know this formula, we are safe to calculate the pressure drop FLG square by equivalent diameter into 2 times rho. So we know the values, we just have to plug in 2.038. L is known as 750, G squared we know, and other parameters are known, and we get a pressure drop of about 6.6 kilopascal. Is that okay?
Yeah, okay. Once again, please show the Reynolds number calculation.
Last here. Is that okay? Okay. So you can follow these books. I have taken mostly from the last one, and also cryogenic systems by Baron. That was in 1985 textbook. That was written only by Baron. Thank you for your attention.
Thank you, sir.